Now this example should help us understand all of those terms. A ball is projected vertically into the air by a ball throwing machine on the ground. Okay, so imagine this is going straight up vertically. It's not going along at all, just straight up, and then when it gets to the top of its flight, it will come straight down. So it will land in exactly the same place that it left. Answer these questions by studying a graph of the ball's displacement, x, over time, t. So first thing to note here, we've got displacement on the y-axis. We always have the units listed. And then time with the units is on the x-axis. So we can quickly and easily see a bunch of basic things about this flight. Now, my first note here of caution. This is the main thing that can get confusing in this topic. This is not a side-on view of the flight of the ball. It's really easy to look at this and think, oh, ball's gone up in the air here and it's gone along through the air and it's landed further away, because it sort of looks like the flight of the ball. Remember what's written here, it's projected vertically. It's going straight up and straight down. It's not going along at all. So all we're doing here is we're measuring after a certain amount of time. It's as though we said, all right, where's the ball now? Well, after a second, it's 15 metres in the air, straight up from where it was. After 2 seconds, it's now 20 metres in the air, and it gets to its top turning point there and must start going back down again, because then when we keep time ticking along, its displacement, or its distance away from where it started, is now going down, which means it's coming back towards the place it started at. And the whole flight takes 4 seconds. So I've got here some questions. What was the maximum height of the ball? Well, greatest height that it reached was 20 metres. That's quite straightforward. How long was the flight? We can read here along the x-axis. It left at 0 time, or 0 seconds, and it got back at 4 seconds. So the whole flight was 4 seconds long. So those two questions are easy. Find the average velocity for the upwards part of the flight. Now, we know that velocity, if it is going to be displacement over time, and we know that speed, if it's distance over time, is going to be something of a rate. So considering that we've just studied calculus, it's really natural and normal to confuse two things here: instantaneous velocity and average velocity. Now we're starting with the thing that's easier, but curiously it seems almost like we're wanting to find the velocity at any one time, but that's for next lesson. Now we can see here that the velocity is going to have something to do with the gradient. If it's going up steeply, then obviously it's gaining a lot of height in a short time, so it must be going very fast. When it slows down and the gradient is lower, or a smaller number, obviously as time ticks along, it's not getting much more height, so it must be going more slowly then. That's a really natural and good observation to make. But what we need to find here is the average velocity for the whole upwards part of the flight. Now it's going upwards from here until it gets to here. This is the time that it stops going up and it starts to go down again. So the average velocity is actually a chord. And you can write that in your notes on your little table that shows how to find average velocity, that it's actually a chord, C-H-O-R-D, that we're going to make between the 2 points of interest. So pick your 2 points. That will be x2, and that will be x1. And of course, this one will equate with the time 2, or we can call it t2. And over here we have t1, which is of course 0. I should probably put that actually directly below t1 there, and let's put x1 there. That makes a little bit more sense. Okay, so average velocity just says, well, what's the displacement? x2 minus x1, it's 20, and we have to keep in mind the direction. It's positive 20, it's gone up. x2 minus x1 is 20 minus 0. So we have 20 metres over the time that it's taken, t2 minus t1. Now in this course, the time is always positive. We sometimes get negative answers for velocity and displacement, but we always consider positive time. We don't go back in time. So it would be a very unusual question in this course that would lead to us needing to graph anything on the other side of the y-axis. Our time taken is 2 seconds. Now, 20 metres per 2 seconds, is that the best that we can express that rate? No, it's nice with rates to express the second thing as generally as 1. Now, we can write this like this as a fraction, 20 metres over 2 seconds, or for every 2 seconds, or per 2 seconds. But we more commonly write speeds and velocities 20 metres per 2 seconds like that, don't we, with a sort of a slash. Now remember, that slash is really just the same thing as that fraction line. And just as with fractions, we can multiply or divide the top and the bottom by any one thing, as long as it's the same thing. To simplify them, it makes much more sense to halve the top and halve the bottom, and we get 10 metres per second. So again, we like to have any numbers that we like at the front there, but we like to have this technically being 1. So think what you need to divide your number by to get 1. Sometimes you might need to multiply it, and do the same to the top. That's how you simplify your rate. So on average, this ball was travelling at 10 metres per second. That was its average velocity. Obviously, sometimes it was going faster than that, and at other times it was going slower, but that's the average. All right, find the displacement in the first second and the third second. Well, displacement takes into account the direction, doesn't it? Let's get rid of that so we can look at our next question. Now in the first second, it travels from here, 0 displacement, to, let's have a look, looks like about 15 metres. So it's travelled 15 metres in a positive direction. So 15 metres is our answer. What's the displacement in the third second? Well, this is the first second, the second second, and this is the third second here. So make sure you don't get mixed up. The third second doesn't mean from the 3 to the 4, it means from the 2 to the 3. And if you need to, just count your columns, count your seconds, or whatever unit you have. Now, here, it was at, this will be our x1, because this is where it started at the beginning of the third second. And by the end of the third second, it looks like it was level with the 15 metre mark again. So it actually went from 20 metres down to 15. And our little formula says to do the second position that it was in minus the first. So it's travelled 5 metres, but it's gone down. So it's actually negative 5 metres. That's the displacement. If you were asked what the distance travelled was in the third second, you'd just say 5 metres, but the displacement, negative 5 metres. All right, find the average velocity in the second second and the fourth second. Well, velocity is the one that takes into account the direction. So if we're going up, it's going to be a positive number. If we're going down, it's going to be negative. So in the second second, we went from here, let's get rid of these bits that we used already, from here to here. So our a change in position, this is x1 and this is x2, we've gone 5 metres up. So we've gone, let's write it over here, we've gone 5 metres in 1 second. Now that's already a nice simple rate because it's got 1 second as the second thing. So I don't have to simplify it like I did with this one. I can say the average velocity was 5 metres per second. And what was the average velocity in the fourth second? Sorry, that's a little bit hard to read there, isn't it? Well, the average velocity in the fourth second, it went from here, let's get rid of our 2's and 1's, to down here. So it actually dropped 15 metres. So the displacement is minus 15 metres, and it all happened in 1 second. So we have minus 15 metres per second. Now, if you were asked what the average speed was in that fourth second, you'd just say 15 metres a second, but the average velocity, minus 15 metres per second. And the last question, compare total displacement with total distance. Well, the displacement from the start to the finish, we'd say this would be x1 and this would be x2. We've gone from 0 metres to 0 metres. The ball is literally right back where it started. So the total displacement would be 0 metres. And yet you can see that stating a displacement like that makes it look like nothing's happened. And therein lies your whole idea of why we sometimes like to include the direction, because it really is informative, telling us if something's going up or down or whether it's going left or right. But other times the total distance is a lot more meaningful. This ball's been somewhere. Well, how far has it been? It went 20 metres up and then it went 20 metres down. So it's travelled 40 metres altogether. but the total displacement, 0 meters. Now, if you're finding the total average velocity for the entire flight, you would get 0 meters per second because it's gone overall nowhere. The total displacement is 0 and the time taken is 4 seconds. But of course, if you do 0 meters for every 4 seconds and divide the top and bottom by 4 to get meters per second, 0 divided by 4 is still going to be 0. So its average velocity is 0. The average speed, on the other hand, would be 40 meters in 4 seconds, which averages out as 10 meters per second, which you can write like that, or you can write per second like that.